You've been hacked. Those three words can be the absolute gut punch. When you see them, any sense of safety and security is torn away. Whether it's your private messages, your social media passwords, your bank information, your company documents, or anything. The implications of messages that were previously private being made public are a terrible feeling with potentially serious consequences. So it's little wonder that genuinely unhackable encryption is a highly sought-after technology. And China could be pointing the way to just that. How? Because of a small Chinese satellite, a record-breaking experiment, and a new, exciting technology, one based on that magic word, quantum. And as scientists say, the approach China employed, quantum key distribution, has the potential to be unhackable because of the underlying principles of quantum physics itself. But what is really happening behind all the hype? Are we actually at the beginning of an impenetrable secrecy for eternity? Or will that mysterious term, quantum, be the demise of secrets instead? Join us today as we cut through the fog and the mystique surrounding the new age of quantum satellites and communication, and uncover precisely how quantum encryption might forever alter our world. Secrets to keeping our messages hidden have existed for over 1,000 years, just about as long as human beings have had written secrets. Julius Caesar, for instance, employed a cipher in his messages so that they would look like meaningless nonsense to an adversary, yet they could be decoded with ease by his generals or friends who were privy-trick. The concept Caesar applied was basic. For each letter of the alphabet, he merely swapped the letter with another letter, a certain number of spaces further. Down or up the alphabet. For instance, if he shifted everything 3 spaces to the right, then A would become D, B would become E, and so on. X would be wrapped around the alphabet to equate to A. Thus, Caesar could maintain important information, confidential, scrambling sentences such as this. But provided that you were aware of the number of spaces he'd shifted the letters over, in this case 3 to the right, then you could simply shift all of it back to unveil the real and significant message. Astrum is great. In this instance, that one item of information, 3 to the right, is the key by which you can unlock the cipher, and encryption has been taking advantage of this same fundamental principle ever since, albeit with a little more complexity. Unfortunately, this cipher has an obvious weakness. There are not that many letters in the alphabet, only 26, so if you came across a message encrypted with Caesar's cipher, you could try moving everything along once, then twice, and so on until the words started making sense. At worst, you'd only have to attempt to move letters 25 times and you could break Caesar's code. It would only take a few minutes before you knew you were on the right path. This type of encryption hacking is referred to as a brute force attack. Guessing at the key over and over again until the encryption rests decoded at your doorstep. It is a reasonable tactic, as long as there are not too many possibilities of what the key might be. Naturally, encryption masters in the past figured out more and more sophisticated methods of mixing up the letters to make it increasingly difficult to break through sheer brute force. For example, why leave all the letters of the alphabet in sequence? Keyword ciphers do not care about that. This second form of cipher operates on the simple basis of just choosing a keyword and then arranging the rest of the alphabet in their usual order following that keyword. With the resulting jumble as the initial point of your cipher refers to the fact that a code asterisk breaker will never be able to defeat your code by merely shifting everything along. Now, they'd have to know the keyword, or do they? In fact, with enough patience, this kind of encryption remains crackable even without the use of the key. Naturally, there are around 403 septillion ways you might rearrange the alphabet, which of course would take way too long to attempt each one on a one-by-one basis. If you attempted one would take longer than the entire history of the universe. But it is technically crackable, still be brute force. If you knew a method of accelerating this guessing process, it would take humans far too long to do something like that. But as soon as the computer was developed in the early 19th century, encryptions, which were not strong enough, might fall to computers guessing much, much quicker. And if a human guessing would be like a hammer banging on the door, computers are jackhammers. Today's CPUs can make billions to trillions of calculations per second. Although it would still take a computer a long time to crack a keyword cipher, trillions are far less than septillions after all. This time can be consistently reduced by bringing more computing power to bear. There is a fear that government. Agencies like the CIA have secret supercomputers with endless CPU brute forcing their way through the encryption of messages. To combat this, modern encryption does not specifically rely on ciphers anymore. Instead, many types of encryption, such as the widely used RSA crypto asterisk systems, rely on complex mathematical problems for which there is no known algorithm a computer can use to solve them. RSA works by taking two massive prime numbers and they multiply them together. The product, referred to as the modulus, is one of the public key that is being shared with others. In order to decrypt the encryption, a hacker must be aware of which two prime numbers were used in generating the modulus. And since there is no easy way to factor it back into the prime numbers, even a supercomputer will have trouble. In the end, the mechanism behind encryption has grown more complex, but largely operates under the same general concept. Messages are scrambled by confusing them up based on some type of rule, and if you have some sort of key, the message can be decoded. Technically, those messages are decodable by brute force methods even without the key, but the keys have been so advanced that even with very powerful supercomputers, brute force methods allegedly would require thousands of years to work. So, our messages are secure then? No, because there's a vulnerability point. If you want to decode an encrypted message, the message sender still has to provide you with the key. If this key can be read by someone in between, the encryption can be reversed without any requirement for brute force techniques whatsoever. And so we look to quantum encryption and what China recently accomplished with the MOSI satellite. For 4 decades, scientists have theorized about a method of sending encryption keys that is completely, irrefutably unhackable. Very cleverly, they don't rely on simply being too complicated for hackers to bother, but rather utilize the fundamental principles of the universe. The principles of quantum superposition and uncertainty. We know that particles, though they seem to be solid and unchanging up here in the ordinary world, act very strangely on a sufficiently small scale. Whereas things such as how fast are you going and where are you are very simple to measure for a traveling macro object such as a spaceship, we have come to realize that we cannot actually know both the speed and position of particles at a quantum level at the same time. At least not without a good deal of uncertainty. This is known as Heisenberg's uncertainty principle and is a proven fact of quantum physics. Weirdly enough, we also know that once the particles are observed, they fall into one of the two states. It has been demonstrated via experiments, such as the double-slit experiment, that one particle can follow more than one path simultaneously and only falls into one path or another after it is measured. Until that moment, it travels down both paths in what is known as superposition. Left and right. Like Schrödinger's famous cat, neither alive nor dead, until the box is opened and it is seen. These principles of quantum physics make it so that once a particle is observed, it behaves differently from when it is not observed. And in the early 1980s, scientists realized that you could integrate this into a very secure means of sending encryption keys. If you translated your encryption key into something tangible, a stream of photons, and designed a clever enough system, it would be feasible by way of statistics to look if your photons had been observed or not between the sender and receiver of the key. That is, it would be possible to look whether some unauthorized hacker had intercepted your encryption key during transit, written it down, and then sent it forward to its original destination, hoping to go unnoticed. As according to the laws of quantum superposition, the instant such observation was made, the key would quietly change, and this change would be identifiable with the right information. And information is power. If you are aware of whether your encryption key is being seen or not, you can delay sending the private message until you have confirmed you have an unobserved key. The message itself can then be safely transmitted through the regular channels. This is brilliant. Of course, getting particles to travel long distances in a state of superposition is not actually very easy. If they bump into an atom along the way, it could collapse the superposition. But scientists came to the conclusion that this issue could be reduced to a minimum if most of the travel was accomplished in a vacuum. Or in other words, if the particles were transmitted throughout space. And it is China that initially brought this hypothesis into practice. Just 1 month ago at the time of writing. On the 19th of March 2025, Chinese scientists announced they'd broken a record for using a satellite to distribute a quantum key between Beijing and a South African university near Cape Town. To do it, they used a tiny microsatellite called MOSI, which transmitted pairs of entangled particles across the vast 12,900 kilometers gap. Each pair of entangled particles had a chance of collapsing during transit, but with enough pairs, receivers at both ends could compare portions of their code and statistically confirm that their particles, and therefore the key they were transporting, were either measured or unmeasured. MOSI weighs only 23 kilograms, an order of magnitude less than past efforts at a quantum satellite, and the successful completion of its mission paves the way for an entire network of distributed, interconnected quantum satellites transferring quantum keys around the globe so that citizens can exchange messages in security. Ponder a world in which every financial transaction, each email, and the whole internet was totally unhackable. where real privacy was an absolute fact of life, courtesy of foolproof encryption. For those who appreciate such privacy, it will be a paradise. Or will it? Is it all a bit too good to be the case? There is one aspect of this that makes me uneasy, that no one's really talking about. Quantum key distribution is done through satellites disseminating quantum keys which are entirely unhackable. All fine and dandy. But look at what I'm doing. There. They disseminate the keys, not the messages themselves. In my investigation into this topic, I have consistently already seen the claim that the encrypted messages can be transmitted securely over the usual channels, because you can check through quantum key distribution that nobody has caught your key. They do this because quantum technology is still not very good at transmitting large amounts of data. A small key is okay, but a larger file is better transferred in the usual way. This is extremely clever and appears logically very sensible. But how is this in any way safer from brute force attacks than encryption is now? Brute force attacks operate by guessing keys one after another. They do not operate by intercepting keys. Naturally, there are hacking techniques that succeed by attempting to intercept the key, since this is much simpler than the enormous amount of computation involved in brute force. But if you do happen to have a very powerful computer, I've not seen an explanation for why you would care whether the key is quantum or not. Either way, it's the encryption itself that is the defense, not how well you've hidden the key. I also imagine a world where hackers don't care if they're noticed or not. While this would mean that the secret message was never sent because a safe key was never found, if hackers simply focused attention on a satellite, it would effectively deny the owner use of that satellite. A denial of service attack, which is an evil way hackers bully individuals into handing over what they need. Suppose that your extremely costly quantum satellite could be made a useless clump of metal because too many messages were being intercepted. Overall, quantum encryption is still ironing out some of the wrinkles. But if you'd like to surf the internet behind a secure layer of encryption today, the sponsor of today's video, NordVPN, is great. Their encryption is strong, making it much more difficult for hackers or advertisers to see what you're doing on the internet. They can also keep monitoring the dark web for you at all times, so if some of your information does leak, you get alerted and can update your passwords. But first and foremost, NordVPN is a VPN, the world's fastest VPN, meaning it allows you to view content from any nation, whether or not they're region locked. So if you don't want to wait for a quantum satellite to encrypt your data, and as I was explaining, those are slightly fishy anyway, scan my QR code or click my link in the description below. Applying my code Astrum at checkout will provide you with 4 additional months on NordVPN subscription and will support the channel directly. But returning to my initial issue, yes, you can argue that the majority of individuals do not possess access to advanced supercomputers. So for most hackers, brute force tactics just aren't on. But there is a new technology emerging that could turn all of this around. And it is also employing that magic word, quantum. Experts think the first available to the public quantum computer is a decade or so away. Quantum computers aren't going to replace all classical computers. They're a little niche and some general. Everyday things like surfing, the web are really just as quick on a classical computer as they are on a quantum one, but due to a quantum computer's power to calculate with qubits that can exist in all kinds of superpositions simultaneously, instead of just 1s and 0s that are either 1 or 0, there are some very particular jobs. Quantum computers are many orders of magnitude faster at. Spookily fast, and one of the jobs it's predicted they'll be faster at is cracking encryption by brute force. And this is no theoretical technology. Quantum computers exist now in the possession of giant corporations and states. In 2015, Google announced that its D-Wave computer had tested 100 million times quicker at doing specific things than an ordinary desktop computer. For comparison's sake, it allegedly did in a second something that would take an ordinary computer 10,000 years to accomplish. Consider the implications of that. Modern encryption is only safe from brute force methods because encryption is so complex nowadays would take a supercomputer thousands of years to work through all the possibilities for keys. But what happens when quantum supercomputers get into the hands of every hacker out there? When those encryption methods, praised for being safe because it would take thousands of years to break, can be broken in seconds. Overnight, no standard. Encryption is secure any longer. This isn't me being a scaremonger. The US government is also afraid of this. The National Institute of Standards and Technology, NIST, which is a government agency under the US Department of Commerce, is worried so much about the coming of this technology that they are warning businesses to begin getting ready for it now by altering the very nature of their encryptions. After all, while quantum computers aren't here yet, there's nothing to prevent hackers from gathering encrypted messages and financial information now, and then just waiting for the day that comes along when they can get their new quantum computer from the stores. Passwords, financial transactions, and certain sensitive messages will still be sometimes relevant a decade from now, and once those messages are all cracked with ease, a wave of crimes and exposed secrets will sweep across the world. But there is hope. NIST has been compiling a defense against the threat posed by quantum computing. And this defense does not lie in unhackable quantum keys, but something more mundane: algorithms. Yes, similar in idea to the algorithms that are protecting encryption already. However, rather than protecting messages by scrambling them with complex mathematical problems that will take a long time to solve, NIST is preparing 5 algorithms that don't care how much computational power you have. For instance, their FIPS 204 standard utilizes mathematical lattices, locations in space with any arbitrary number of dimensions to operate in. The key involves having you identify some specific pattern within such as finding that specific path in a 5D maze. Since there isn't a known mathematical algorithm that can discover this path in an efficient manner, there's no algorithm that you can provide to a quantum computer. They are hard to deal with the additional dimensions, and can't get the problem solved any quicker than a classical computer. In other words, it doesn't matter if your muscles are powerful or not if you don't know how to hammer. FIPS 204 is one example of a quantum-resistant or post-quantum algorithm. Companies such as Nord-Asterisk VPN are already beginning to adopt these types of post-quantum encryption. While it's not entirely rolled out, they're already gearing up for what's next. And we're at the same point we began with. New technology has come around, and both hackers and cryptographers are given the same new toys. Each made huge leaps in their area, but once more, as with the advent of computers, the situation settles. Computers posed a threat to privacy, but then ended up re-establishing it. Quantum technology both enhances privacy and comes up with new means to destroy it. The cycle of history repeats itself, with developers making new algorithms and hackers searching for points of weakness, and every victory on one side encourages the other to attempt all the more. So have quantum satellites opened the 2233 era of guaranteed privacy? I very much doubt it. Even if the key is absolutely secure, hackers can always find an alternative route in. But also, has quantum computing knocked down every defense and ended secrecy forever? I also find myself skeptical. Brute force might soon be more effective as a hacking tool, but already companies and governments are pivoting to new defenses that can weather the coming storm. But who can say for sure? Right now, the future is in a sort of superposition of its own, both secure and unsecured, private and public. And similar to all things quantum, that superposition will only reduce once it has been experienced firsthand. Thanks for watching.